Hello everyone, welcome back to Tanisha's Concept Corner. So we were doing this chapter ray optics and optical instruments in physics. In our previous video we covered till this particular part, so let us proceed further with these example questions. So this question over here says that suppose there is a concave mirror and I cover the lower half of it, then what will happen to the image? So let us assume this is our concave mirror. I cover some part of it, the lower half of it, with some material that is not going to allow reflection. So suppose I place my object over here. You might think, okay, you covered the lower half of this mirror, so what will happen? Image will appear only half. But that is not the case, because over these points the loss of reflection will still be true. If it is coming parallel, over here it can still pass through focus, and angle of incidence will be equal to angle of reflection. There is no problem in that. Over here also it can pass, or then passing obliquely also with same amount of angle of incidence, it will get reflected back in such a way that angle of reflection should also be equal to that. Image can be formed over here. There is no issue. It will be a complete image only, because here loss of reflection will still be the same. The only thing that will change is intensity. Before, what used to happen, before I covered this part, another rays also used to come over here, and here also reflection used to happen. But now that we have covered this part, there will be not many reflected rays. So intensity, how bright that image is, that might decrease, but it doesn't mean half of that image only will be shown. Many number of rays are needed to form the image, because many incident rays will be coming, but we generally represent it with two rays only. With that also image can be formed. Those two rays can be here, this two rays can be here, and here much more surface is actually available for many incident rays to pass also. So there will be no problem in forming the image as a complete one, but only its intensity will reduce. Minimum 2 incident rays are needed in order to form that image, but there actually many rays only can come. So there is no issue in forming the image, only the brightness will decrease because many of the reflecting rays are not there. Now the next question is that suppose mobile phone is lying like this at this particular part. They're saying that magnification is not uniform. Why is this happening? Why my image is like this? This is the object and this is the image, and as usual, incident ray being parallel, then it is passing through focus, obliquely passing like this, then with the same amount of uh, angle of incidence, angle of reflection will be required. Passing through focus, then it will emerge parallel. Passing through focus, it will emerge parallel. So all these they have followed, and finally wherever the rays are meeting, they drew the image, and they are saying that its magnification is not uniform. Over here it's being same, over here it got magnified too much. Why is this happening? Again the rules. Whenever object is kept at center of curvature, real and inverted image will form, but it will be of same size. Okay, but again, what about the rest of the part of the phone over here? It is between C and F, meaning beyond C the image should form. If it is at center of curvature only the image will form. If it is between C and F, it will form beyond C. And what is the rule? If it is between C and F, beyond C and magnified. So this particular part is magnified, and this particular part stays over here and it has the same size. So because of these rule only, its magnification is not uniform. The next question, suppose object distance is 10 centimeter, then it is 5 centimeter. Concave mirror, then radius of curvature is given. They want to find out about the image. Now it is concave mirror, so focal length should be negative. If it is concave mirror, focal length will be at the front of the mirror towards the left. So left side is negative. So that's why focal length should be negative, and they have given r. They didn't directly give the focal length, and we already know the formula we derived in our previous video also. F is equal to r by 2. So they found the focal length. We already know the object distance negative 10 centimeter. Then how do we find out v, the image distance? The mirror formula, 1 by f is equal to 1 by v plus 1 by u. Please keep in mind the sign convention. Object distance will always be negative, because object will always be placed in front of the mirror. That means towards the left. No matter concave, no matter convex, it is always placed in front of the mirror, because you can't place the object behind the mirror, and in front of the mirror meaning it is always towards this left. So it is always negative. So you put the negative signs, we can just rearrange these numbers and we can get V. We got negative 30 centimeter. From here only we can see if it is negative, that means it's same side as the object, because object distance is negative. Negative meaning left side. So same as side as the object, meaning if it is left side, it is real and inverted. If the image is forming over here, because we know in concave mirror only one case virtual and erect will form over here. Virtual and erect is forming over the right side. So if it is towards the left side, because it's negative meaning it's left side, I can easily get to know it's real and inverted. If it is real image, it will always be inverted. You cannot say real and erect. So we got from here itself, we can find that out, and magnification formula also you can use to find it. Minus V upon U. Minus V upon U is the formula. Then V is minus 30 centimeter. We found out over here. U is minus 10 centimeter given. Then we got minus 3. Whenever magnification is negative, it will be real and inverted. And because it is 3, it is being magnified. If it was something like 0.01 or something, then you will write it's diminished. And further, for 10 centimeter you calculated. For 5 centimeter also we have to calculate. Same thing. U will be negative 5 centimeter. And F we have calculated from R by 2. Again, you can rearrange the numbers. If you send this over here, it will become, this is negative 1 by 5. So if you send it over here, it will become positive 1 by 5. You can take LCM and find that out. Then take inverse, because it's 1 by V. If you get it inverted, then you will be able to get the image distance. Again, from here only you can see, if it is positive, that means it's towards the right side according to our sign convention, and that means it is virtual and erect. If it is virtual, it will be erect only. You cannot say virtual and inverted, that is not there. So virtual and erect, and minus V by U after finding out. Over here also you can see magnification should be positive. If it is positive, it is virtual and erect. This is one way to check your answers also. If you're getting positive over here and your understanding from here itself is that okay, it's towards the right, it is virtual and erect, magnification also should come positive. If you're doing some mistake, then you can check over here itself, and it should be magnified. You cannot get some other 0.1 like that answer over here. How will I know that it's magnified? Because in concave mirror only one scenario is virtual and erect, and that is when it is between focus and pole. It will form over here and it is magnified. In entire concave and convex mirror, only one scenario where virtual image is getting magnified is this only. Because in convex mirror, virtual image is formed, but it is always diminished. Two cases were there. So with that, we can find it in this manner. Now this is an important question. Suppose while sitting in a parked car, you notice a jogger approaching towards you in the side view mirror. Now they directly didn't mention which mirror, but we only have to understand that side view mirror is a convex mirror. Because if you're sitting in a car and there is mirror, if it is a concave mirror, you would see inverted images, because in most of the scenarios in concave mirror, inverted images are only formed, but you don't see people running behind you and car coming behind you is inverted. While traveling in a car also, you look at the mirror, they won't be inverted, right? That doesn't make any sense. Only in convex mirror, in every single scenario, virtual and erect images will be formed. So obviously this is a convex mirror, so they might directly not mention in the question, but we have to pick it up. R is equal to 2 meter. Now suppose jogger speed is given, then how fast the image of the jogger will appear, and they have given different object distances, like jogger can be considered as our object. Alright, so how to solve this question? Suppose jogger is first at 39 meter away. Then we are using mirror equation only again. 1 by F is equal to 1 by V plus 1 by U. We just rearrange it to get this formula. You can just put the values like over here itself. In this format only you can put if this is confusing. But here they just have rearranged over here to get V is equal to this. Now this is convex mirror. So focal length should be positive, because convex mirror principal focus will be towards the right side, as over here. Yeah, in convex mirror, center of curvature, principal focus will be over here. It will be towards the right side, so it is positive, and we can find that out again using the same formula. F is equal to R by 2. So 2 by 2 is 1 meter. So we have put that, and object distance will always be negative. So put it, then you will get the image distance. Now our work is still not done because we need to find how fast, meaning they are asking the speed of the image. Because jogger is not just fixed at one particular point, he's continuously running, right? Okay, first he was at this position, then we got the image distance as this. Within 1 second, again he will be somewhere else because he's continuously moving. So let us say after 1 second, where will the jogger be? How do you calculate? Nothing but this is time and speed is given. You need the distance. Speed is equal to distance upon time. Speed is equal to distance upon time. So in 1 second, where is he moving? How will I find? Speed is nothing but phi. It is given there. Distance is what I need to find out. And time is 1 second I'm taking. For my convenience, let us say after 1 second, where is the jogger? 5 meter. This is his distance. In 1 second, he is running 5 meter. So that is what. Initially, he was at this particular position. Then he moved 5 meter further. So I have added it. Now this is his position. Now this will become your u. With this you calculate v now. Same formula only. U negative 34 into 1 negative 34 minus 1. So negative 34 negative 1 will become negative 35. If it is negative 35 and here negative 34 into 1 is negative 34. Negative 34 by negative 35. Negative negative will get cancelled. You will get 34 upon 35. Same formula you can put. Okay, now this is the new position of that image. So it is basically something like this. If we want to understand through this mirror, you can consider a convex mirror. If we consider this convex mirror, we can say, suppose jogger is somewhere over here. First he was at negative 39. Because jogger is our object, he can be considered as towards the left side, towards the front of the mirror. Then he will run further and he will come over here. Okay, so suppose at first the image is formed over here. Virtual and direct images will be formed, and then the image will be formed over here, because in convex mirror two only scenarios will be there. One will be towards infinity, then it will form at focus, but generally here we are not considering it at infinity. Let us say somewhere f is over here. Anywhere if it is not towards the infinity, the image will always form between pole and focus, and they will be virtual and erect. So initially the jogger was here, then he is running and coming over here, then image first it will be formed here, then it will be formed here. So these two locations you got now, you found out. Initially was at negative 39, then he was at 34, then what was the image distances in both the scenarios? We found out that 39 by 40, then 34 by 35. Now we need to find the distance between those 2 points, because you need to find out how fast the image is traveling. That means image distance you need to travel. That means image distance will be between these both points. How fast the image is going, meaning how much distance is the image traveling with the jogger. Jogger is traveling like this, image is moving from here to here. So how do you get that? You got this particular image distance that was actually measured from the pole. Generally image distance is measured from the pole, whatever you found out. So you found out first scenario like this. In second scenario, when jogger came further, you found out one more image distance, and that will be this. You're always measuring from the pole, but you don't need these image distances. You need the distance that the image traveled, because you need to find how fast the image is going, so that I can do distance divided by time. So here don't get confused. Image distance that you're finding is from pole to that image position, but I am asking about this image distance, like initially where the image is and after that where the image is. Between these 2 points, what is the distance I'm asking? Because you need to find the speed. Distance upon time you have to do. How will you find out? You found out this distance, you found out this distance. If you're going to subtract these both, you will get the left out part. That is what is going to happen. From this part, if you're going to remove this much part, you will get the required distance. That is what we are doing here. So initially was this, then finally we are getting this. We can subtract both of them. You can get the between those 2 points how much distance is. This is the distance. This is actually the distance traveled by that image. For till now the scenario is like after 1 second we are considering. So this image will also will travel in 1 second only. So this is the distance divided by 1 second. That will be nothing but your speed. Distance divided by time is our speed. So this is the scenario. Same thing we can do for 29 meter also. First consider 29 meter, that will be negative 29. Put it in the formula to find out V. After finding out V, again negative 29 plus 5 because the jogger is running. Initially he was at this position. After that again he traveled 5 meter. You got one more particular answer. Again put that will become your object distance because now the jogger has moved to new location. That will be kept in this particular formula. You will again get another V. Subtract those both V's. First it will be minus 29 meter. Then find V. Then add minus 29 meter plus 5. Now with that object distance you will again find V. Whatever you got both the V's, you will subtract them. And this is only happening for 1 second. So by 1, that means you can simply write the distance itself and put meter per second. That will be the speeds. So they have found it. So this is the questions. Now let's start the new topic, that is refraction. What is refraction? Whenever light encounters some other transparent medium, generally a part of it will get reflected back and the part of it will move to the next medium. Whenever that is happening, the direction of the light will change and the speed will change. Consider the ray of light as a beam. Generally beam meaning many light rays will be there, but if you're going to draw many light rays it will become confusing for us. So they're just considering a ray of light and telling that that will only represent a beam. Now the perfect definition they're giving is that the direction of propagation of an obliquely incident, meaning the incident ray, it should be between 0 to 90 degree angle if you're going to provide. Then the light will enter some other medium, whatever you have kept. Like here we have kept a rectangular glass slab. What will happen? It will change. What is changing? The direction of propagation of that incident ray will change at the interface of the two medium. That is refraction of light, the bending of the light ray. Whenever you put any pencil in a transparent glass filled with water, you can see how the pencil is like slit. It appears to be slit, it appears to be broken. So that is all because of bending of this light ray only. Incident ray is coming, a part of it will get reflected back, a part of it will move through this medium, and actually this is a optically denser medium which we will be studying over here. So whenever that is happening, this direction will change because the speed of light is changing. So it will cause the light to bend, it will cause the light to change its direction. That is nothing but refraction of light. Now Snell experimentally obtained this following laws. Just like law of reflection only, here also in law of refraction what is there? Incident ray, refracted ray, not reflected, refracted ray, and the normal to the interference at the point of incidence all lie in the same plane. Same like law of reflection only. That means suppose this is my screen, incident ray, reflected ray, normal, refracted ray, everything is going to be in this particular plane only. It won't come out of my screen if this is happening. That is what they mean. So incident ray, refracted ray, and the normal, everything is lying in the same plane. Reflected ray also, if a part of it is getting reflected back, then that will be like that. So if it is happening like a 2D dimension or something, then it is not going according to 3D. This is 2D. So it won't come in 3D plane. It won't just come out of my screen. That is what it means. Then one more law is that if you take sin I by sin r, it gives a constant value, that is n to 1. This is nothing but called as refractive index. So that is what sine of angle of incidence to the sine of angle of refraction, if you take, it will be constant. Remember that the angle of incidence and refractions are the angle that the incident and its refracted ray. Okay, this is normal. So whatever incident ray is there, between incident ray and normal, you get the angle of incidence, and between this normal and the refracted ray, you get the angle of refraction. Now, for a given pair of medium and for a given light color, whatever color is there for the light that is passing, for that this value will always be constant no matter whatever your angles are changing. So given pair of medium meaning if air and glass slab you are taking, consider that only, don't change the medium. And suppose your light is in green color or yellow color, consider that only. Now take different angles. You're going to give the instant ray, for example, you are taking some laser light or something and you're pointing it. First it can be towards 30 degree, then it can be towards 40 degree, anything, and you measure the refracted ray that is obtained also and put it over here. Every single case you will get a constant value, approximately constant also, while you're doing the experiment. So that is nothing but the refractive index. And this refractive index generally it depends upon the wavelength of light, but it does not depend upon the angle of incidence. Angle of incidence can be anything. You can point the laser at anywhere, but it depends upon the wavelength. Now suppose this n to 1 is greater than 1. Whenever this is greater than 1, remember numerator will be greater than the denominator. So sin I is greater than sin r then. That is nothing but I is greater than r. When this is happening, when I is greater than r, that means r, this refracted ray is actually moving towards the normal. It is passing from rarer medium to denser medium. Now rarer and denser medium, it's not like any normal density like mass by volume. This is optical density. Optical density is nothing but the ratio of speed of light in two media. How is the speed getting influenced based on that? It is not normal density. Okay, so some materials like might have more density, mass by volume will be more, but their optical density may be less. That's what they've given over here. Mass density of turpentine is less than water, but its optical density is higher. Whenever optically denser medium if you take, that is nothing but where speed of light reduces. So compared to air, if you take a glass slab, in glass slab air's the light's speed will reduce. So this glass slab will be more denser. So optically denser medium, and the other medium where the speed of light will be more, that will be called as optically rarer medium. So when you calculated this value and you found out that n to 1 is being greater than 1, that means numerator is greater than denominator, sin I greater than sin r, so obviously angle should be greater, I is greater than r. I will be greater than r meaning refracted rays going towards the normal, it will bend towards the normal. That means it is entering from rarer medium to denser medium, and in denser medium the speed of light is reducing. Now exactly opposite, if you take n to 1 is less than 1. Whenever this is less than 1, denominator will be greater. So sin r is greater than sin I, then r will be greater than I. If r is greater than I, what will happen? Refracted ray will move away from the normal. If it is moving away from the normal, you can guess that it is from denser medium to rarer medium it will move. Optically denser medium to optically rarer medium it will move, and speed of light will increase. This is what we can find from the law. N12 is inverse of N21. N12 is inverse of N21. Generally N21 is nothing but N2 upon N1. Refractive index of medium 2 by refractive index of medium 1. We can also say this is equal to V1 upon V2. What is V1? Speed of light is speed of light in medium 1. V2 is speed of light in medium 2. Why is this? Because it is inversely proportional. Because if refractive index is more, if refractive index of the material is more, speed of light will reduce. That's why whenever you're talking about inverse, you will interchange the numbers and write. So for medium 2, you will equate it with the speed of medium 1. For medium 1, you will equate it with the speed of medium 2. Remember, refractive index is always inversely proportional to the speed. This is one thing. And N21 is inverse to N12. Same thing, because N12 means N1 upon N2. If you take 1 upon this, you can again make it reverse. If it is coming to the numerator, then it will become N2 upon N1. That is the same thing as N21. So that property they are talking about over here. Now, as we already know, again incident ray is coming over here. This is the glass. So here speed of light will reduce. So glass is more denser than air. Air is the rarer medium, glass is the denser medium. Incident ray is coming like this. You can draw normal. Wherever the incident ray is touching the glass, you can draw normal, just horizontally. Then what will happen? It should move towards the normal, because it's entering the denser medium. Then again here one more side is there. So this refracted ray will act like incident ray to this particular side. Then what is happening? Again normal you can draw wherever it is touching. Now glass and air, where will be the speed of light more? It will be at air. So now here it is moving from denser medium to rarer medium. In such a case, speed will increase and it will move away from the normal. See, here it is moving closer to the normal and here it moved away from the normal. And here I'm just writing dotted lines. I'm just extending this incident ray only. What if I didn't keep any medium in between? Then it will just move straightly like this. And whatever refracted ray it is finally coming out, and your incident ray after you extended it with dotted lines. I'm just representing the path of light. How would it be if there is no medium at all? It will just move straightly, no? So these both, it is found out that they are actually parallel. There is no deviation at all. Only thing is that there is a slight displacement between these two. You call that as lateral shift or lateral displacement. And one more thing is that I1 is equal to R2. Now if they ask the reason for this, you can say that this rectangular glass slab which is there, opposite sides are parallel. So normals are exactly horizontal to this. So normals will also become parallel, and you can say these are alternate exterior angles. It will be something like this. Normals are parallel. You can prove by saying that rectangular glass slab is there, so opposite sides will be parallel. And you know our normals are being exactly horizontal like this. So obviously these both will also be parallel. So that is what is happening. So if I draw these parallel normals, if I draw these parallel normals like this, then there will be one line passing like this. You will nothing but get alternate exterior angles. This will be our I, this will be our R. Alternate exterior angles will be equal. So that's why R2 is equal to I1. And emergent ray, this is this refracted ray, whatever is there, this is emergent ray, that will be parallel to the incident ray. There is no deviation, nothing exactly, they are parallel. There is no it's not deviating in other direction, they're exactly parallel. Only thing is that there is this displacement there. Another applications are given here for refraction, saying that for example, suppose there is this tank that is filled with water, and let me keep any object over here, any coin I can keep, and when I look from here, that object or that coin that I keep appears to be higher. It's I cannot see properly that it's clearly kept at bottom. This is called the apparent depth. From here to here, this is the apparent depth, and this is the real depth. Coin is actually over here, but apparent meaning where it appears to be. So what is happening over here? It is moving from denser medium to rarer medium. The rays are moving. So what will happen? First you can draw two rays like this, and you can draw normal. And then what will happen? You generally know from denser to rarer meaning Here speed of light is less, here speed of light is more, so it will move away from the normal. So draw away from the normal. And generally whenever you're forming an image, the reflected or the refracted rays should be extended, and they have to meet at a point. You can see here, if I just keep extending over here, they can never meet. So in such a case, we always, what do? We extend it backwards. So refracted ray can be extended backwards, then here they're meeting, so this is the image formed. So I'm seeing over here, it is appearing over here. And if I see from sideways also, same thing. Here it is passing without any deviation, and here uh, the two incident rays are moving from denser medium to rarer medium, and they will move away from the normal. And generally the refracted rays should be extended so that they meet at one point and the image will be formed, but here they are not meeting, so one way is to extend them backwards, then they are meeting over here. So I will be able to see slightly higher than the actual position. So this will be the apparent depth. There is one formula to calculate apparent depth, that is real depth divided by the refractive index of the medium. Here real depth is H2. Refractive index will be refractive index of the water. You can get your apparent depth. And one more phenomenon is refraction of light through atmosphere. There are several layers of atmospheres when it comes from Earth to space. So there also continuous refraction will be taking place through whatever atmosphere is there. That's why during sunrise we can actually see sun visible a little before the actual sunrise itself, because whenever refraction is happening, you can see the objects slightly higher above position, you can see them. So what is happening when sun is still at a low, you can see here actual position of the sun is here, horizon is over here, but because of refraction that is happening to the atmosphere, what is happening, it is apparent position is seen above, so we can actually see the sun even before the actual sunrise. Same thing with sunset also, it will happen. So sun is visible before the, and little after the actual sunset. After sunset what will happen, again it will move down, sun is going to go down. It would have even gone down, but still we can see the sun. After the actual sunrise happened also, you can still see the sun, because apparent position is what, little bit above the actual position. So actually there is this 2 minutes delay that is happening. Refractive index of air with respect to vacuum is given, and 2 minutes is what that actual sunset and apparent sunset differences. Actual sunset would have happened before itself, but because the apparent position is slightly higher, you're still able to see. 2 minutes delay will be there. So that is one more real application. Now they are telling that Earth takes 24 hours to rotate once about its axis. Then what about 1 degree shift when viewed from the Earth? So very simple. Entire rotation about its axis is nothing but what, entire circle, that will be what, 360 degrees. So for rotating in that 360 degree, it is taking 24 hours. So for 1 degree, how much will it take? You have to just do division, 24 divided by 360. For 360 degrees, it is 24 hours. You have to calculate for 1 degree, which you don't know. So write it as x. What will you do? You will do cross multiplication. When you do cross multiplication, 360 into x will be equal to 24 into 1, that is 24. So what will be your x? 24 divided by 360. So that is the thing. Now next topic is total internal reflection. One more very important topic. When light travels from an optically denser medium to a rarer medium, it will partly get reflected back into the same medium, and then partly the part of it will get reflected to the second medium. When this reflection takes place, because part of it is getting reflected back and a part of it will be refracted, so that reflection is internal reflection. So we can understand through this, where suppose This is some water medium, a water tank can be taken, and this is denser medium to rarer medium. This is important. From denser medium to rarer medium it will be moving. Now whenever rays are, there will be a number of rays coming from one particular point only. This is denser medium, this is rarer medium, and from here one ray is going, a part of it will get reflected back, a part of it will get refracted. Same thing with other ray. A part of ray will get refracted, a part of it will get reflected. This is internal reflection. Internal reflection. A part of it is not getting refracted, it's only getting reflected. That is total internal reflection. So what is the scenario over here? You have just drawn a normal to understand angle of incidence, angle of reflection, and angle of refraction. Here IC is written. This is called as critical angle. So when the incident ray is suppose passing like this, and so at some angle the refracted angle is exactly 90 degree. Don't think there is no refraction over here. This arrow is shown. When this angle of refraction exactly becomes 90 degree, whatever angle of incidence for that it has happened, that will be called as critical angle. So suppose you have given some angle of incidence as 40 degree, it is moving over here, and then angle of refraction became 90 degree. From that you can get to know that I angle is nothing but critical angle. Now further, if you're going to bend it, if you're going to give angle of incidence greater than the critical angle, then you will get your total internal reflection. So two conditions to get this total internal reflection. One, rays should always move from denser medium to rarer medium. Two, your angle of incidence should be greater than your critical angle. Then total internal reflection will take place. Now normally some fraction will get transmitted, so the reflected ray which is there will be less intense. See over here the ray is moving, a part of it got refracted, the transmitted meaning it got refracted, and this is getting reflected. So this intensity will be less because some part of light is lost over here. But in total internal reflection there is nothing lost because it's not getting refracted. So that the whatever reflected ray is there, it will be more intense. That is what they are saying in this paragraph. And as we already know, angle of incidence that is corresponding to the angle of refraction 90 degree. When angle of refraction is 90 degree, whatever your angle of incidence is there, that angle AO3N, that will be called as critical angle for given pair of media. Now here we are nothing but like giving one formula specially for a critical angle using Snell's law. So what was that? Nothing but sine I will be equal to sine I by sine R will be equal to n to 1. That is nothing but n2 upon n1. Alright, so what we are telling over here is, for critical angle I have to find out. So for critical angle, if I have to find out, our R will be 90 degree, our angle of incidence will be nothing but this, isn't it? Now we can just take the inverse of this, sine R upon sine IC. Sine R meaning 90 degree. When angle of refraction is 90 degree, what is happening? Sine of angle of incidence will be critical angle. It will be critical angle, and this is equal to n1 upon n2. I just took the inverse of this. What is our medium 1? Our medium 1 is nothing but water. Always see where the rays are passing from. First it is passing from water to the air. So our medium 1 is water, our medium 2 is air. So I can write as n12, n2 by n1 is n21, so n1 by n2 will be n12, and we all know sine 90 degree, what is the value for it? It is 1. So 1 upon sine IC is equal to N12. This is the formula. Or you can write it in another way. N21 will be is equal to sine IC. Just taking the inverse. Both of these formulas can be used when you got to know that there is a critical angle. That is what is written here. Now for values I which are larger, basically when angle of incidence is going to be greater than critical angle, total internal reflection takes place, no refraction is happening, no the light is lost into the another medium. Then what is there? Snell's law of refraction cannot be satisfied. Obviously, if refraction is not taking place, there is no angle only, then Snell's law cannot be working because sin I by sin r. There is no r is 0 and denominator is 0, meaning it's nothing but not defined. So Snell's law cannot work if you got to know that angle of incidence is actually greater than the critical angle. Angle of incidence, if it is greater than critical angle, total internal reflection will take place. There is no refraction, that's why Snell's law won't work, and based on that they have given certain values over here. When refractive index, using this we can calculate, right? With refractive index we can actually calculate the critical angle also. So these are certain values given to us. Now if you want to like demonstrate it, and if you want to see through these total internal reflection through certain experiment, one way to do it is you can take any beaker and take clear water in it, and then we can add few drops of milk till like when it becomes little bit cloudy texture, when it becomes like opaque kind of stuff, it becomes fully white, right? We can do that. Why are we doing this? Basically colloidal solution, because in colloidal solution we know, right, we have learned in our previous grades that particles are not very small, they're a little bit of a bigger size, and they can actually scatter the light. So you can see the path of the light and their path, how they are moving properly. So that's why we are taking water and milk combination. Now over here you can see, in first scenario you put up the angle of incidence in such a way that reflection is also taking place, refraction is also taking place. Then you will put the angle of incidence in such a way saying total internal reflection should take place. So that means my angle of incidence should be greater than the critical angle. So you can take some laser light or torch, and you will be able to put it in certain direction from downwards. You can see in your room, if this beaker is sitting on the table, one light ray you can see on the table, and the other somewhere at the roof or somewhere at the side you can see. And if you're going to slightly adjust the angle more, you can only see the reflection below you. You can see, you cannot see anything above or sideways at the rooftop, you cannot see anything. And further, if you're going to take a small uh, like a thinner test tube kind of stuff, and if you're going to adjust it in such a way that you will only get total internal reflection, it will just be bouncing back in this way. So this was the demonstration that is taking place. If really you want to do experiment and find out how this total internal reflection is working, that's why they've given these examples. So further we will cover the other topics in next few videos, and if you liked my content, please like the video, and any doubts and any problems you want me to solve, you can comment, and please subscribe guys. See you in the next video. Bye.